Hello, welcome to this video. Today we're gonna talk about a quite an important theorem in number theory and more specifically in modular arithmetic, called the Chinese remainder theorem. And despite its unoriginal name, it is incredibly useful when trying to solve equations in modular arithmetic. So equations will be something like x is congruent to 2 mod 3 and x is congruent to 5 mod 7. These are equations in modular arithmetic that are from first order, because they're not anything like x squared or something. We do have multiple equations, but the power of x is only 1. We're only talking about x to the first power. And then we might have a list of congruences for x that we want to solve for x being congruent to, for what is x congruent to some number, given all of those congruences. And what we're going to do, will basically generalize these kinds of equations. So let's erase this, and let's now state the Chinese remainder theorem. So it says, if we have k numbers, so n1, n2, n3, so on until nk, which are coprime in couples, which basically means we take any two different numbers from this set of numbers, they will be coprime. So for I different than j, and I am and j are co-prime. So if we have this list of numbers, then we have another list, a list of k whole numbers, which we'll call the remainders. You'll soon see why. So we have k remainders, so R1, R2, R3, so on until Rk. The Chinese remainder theorem says, first of all, before that, I'm also going to label n to be the product of n1 times n2 until nk. Just so everything is easier when we do the actual proof. So, the Chinese remainder theorem says that there exists a whole number x that satisfies x is congruent to Ri, mod Ni for all I which are between 1 and k. So it's congruent to R1 mod N1, R2 mod N2, and so on until Rk mod Nk. And it also says that there is a singular x mod n. So remember, n is the product of all of these, of all of these numbers, which we're doing the which are sort of the basis of our mod equations. So we have n1 times n2 all the way on times nk. That is n. And this, the Chinese remainder theorem says, not only does there exist one, if we take all the ones that satisfy these conditions and we do mod n, we will always get the same number. It's singular mod n. So that's the theorem. The first thing we're going to do is prove that there exists an x, and then we're going to prove that there exists a singular x mod n. So let's now erase the board and talk about the tools that we will need to solve this problem. So for the proof, we will need to talk about inverses in modular arithmetic. So we're going to prove a theorem, or at least sort of a half of a theorem, which says if A and B are co-prime, there exists a number C that satisfies that A times C is congruent to 1 mod B. So this is what we're going to show in a pretty nice way. So what we're going to do is use an algorithm for calculating GCDs of numbers. So this is what we're going to do. We're going to say 1 is equal to the GCD of A and B. That just simply follows from the fact that A and B are coprime. That's the definition of coprime. If A and B are coprime, if and only if their GCD is 1. Now let's just assume that without loss of generality, it doesn't really work here because we can't switch the A and the B here to be the same thing. But let's just ignore what this says first and see A and B are coprime. And then assume, without loss of generality, that A is bigger than B. And remember, it can't be equal to B. And we will assume, without loss of generality, that A is bigger than or equal to B. And yes, almost all the time, in fact there's only one case where when A is equal to B, and that is when they're both equal to 1, because they have to be coprime too. But that's out of the way right now. What this theorem says, basically, even if this doesn't equal 1, so let's quickly ignore this equals 1, it says the GCD of A and B is equal to the GCD of A minus B and B. I'm not going to prove this, it's quite easy to prove actually, but what this allows us to do is continue to making the numbers smaller and smaller and smaller until we eventually have a GCD that is very easy to calculate. And then we'll be able to find the GCD of the original numbers. And now, in our case, when A and B are co-prime, we know that this GCD is equal to 1. And now we'll keep on doing this. So this is going to equal, and then we're going to subtract the smaller one from the bigger one here, then the smaller one from the bigger one, and then and so on and so forth, until we eventually arrive at the GCD of P and Q. And we will assume then P and Q are the smallest they can be, meaning that we can't do the subtracting thing unless without the number turning negative, or we're just staying at the same place. So and what we will show is that one of these has to be 0 and one of these has to be 1. So the first thing we'll show is one of these has to be 0, and then automatically we'll get the other one is 1. So let's assume that P is different than 0 and Q is different than 0. Then, without loss of generality, we can again say, let P be bigger than Q without loss of generality. And then we get that our GCD of P and Q is now the GCD of P minus Q, comma Q. So we just used this algorithm again by its definition, and now this is a contradiction because Q is different than 0, we know P minus Q has to be smaller than P, and because P is bigger than or equal to Q, we know this has to be a non-negative integer. So 0, 1, 2, and so on. Meaning that P and Q aren't the smallest numbers that satisfy this after repeating this algorithm for several times. Meaning that it is the case with that P is equal to 0 or Q is equal to 0. Again, without loss of generality, let's say Q is equal to 0. That gives us that 1 is equal to the GCD of P and 0, and the GCD of anything and 0 is just the anything, the number that you put in with the 0, meaning that this is P. And then we directly got that P is 1, meaning that one of these has to be 1, one of these has to be 0. Now, let's look at this another way. Each time we're doing this, we're repeating this algorithm, we're subtracting either B or A minus B, or some combination, some linear combination of A and B. Something that looks like X times A plus Y times B. That's what we're always subtracting, either from A or B or from another linear combination of A and B. But what we always get is another linear combination of A and B, meaning that along the way, all of these can be expressed as a linear combination of A and B from whole numbers. So X times A plus Y times B, when X and Y are both whole numbers. because all we're doing is adding and subtracting these ones that we had at the beginning, 1, 0, and 0, 1. All we're doing is adding and subtracting in several ways. It's never going to go just something like a half. It can't. We're not dividing by anything. Meaning that we know that even at the last step, so we'll just write that this is the GCD of 1 and 0. Even at this last step, we know that 1 can be expressed as that linear combination of A and B. Meaning that there exists some whole numbers x and y such that 1 is equal to x times A plus y times B. Now, all we will do is mod B. And then, when we do mod B, this entire thing will be 0, and then we'll get that there exists some integer x such that when you multiply it by A, it is congruent to 1 mod B. AKA, its inverse, x is the inverse of A mod B. And that's how we prove that this theorem. Now we will use this theorem to show, prove. Now we will use this theorem to prove the Chinese remainder theorem. Okay, now that we know that we proved the inverse theorem, or at least half of it, because we also need to show that there exists only one mod B, but that out of the way, for this theorem, we only need to know that there exists one. So, here's what we'll do. Instead of immediately looking at R1 mod N1, R2 mod N2, it's a bit hard to get all of those together. Instead, what we're going to do is look at numbers mi that satisfy, that they're congruent to 0. Mod N1, mi is congruent to 0. Mod N2, so on and so forth, until mi is congruent to 1 mod ni, and then again it continues to be 0 until we get mk is congruent to 0, until we get mi is congruent to 0 mod nk. So it's congruent to 0 mod all numbers except ni, and it's congruent to 1 mod ni. Now we know that if mi is congruent to 0 is congruent to 0 mods n1, n2, and so on until ni minus 1, and congruent to 0 mod ni plus 1 and ni plus 2 up until nk, because we know all of these numbers are coprime in couples, we know if mi is congruent to 0 mod each one of these separately, it is also congruent to 0 mod their product. So, now we know mi is simply congruent to 0 mod n1 times n2 times all the way on to times ni minus 1 times ni plus 1, then continue on until times nk. But this will be very annoying to each time again and again write this. So instead, I'm going to write this as n over ni, because that's just what it is. We're multiplying everything except ni. We will call this n over ni, and you can easily see why this is true just when we were to multiply this by ni, we would get n1 times n2 all over 2 times nk, which we defined as n. So this is n over ni. And we also can't forget mi is converted to 1 mod ni. Now this is what we need to solve. And here's how we're going to do it. And here's how we're going to do it. We will look at the number n over ni. We know that n over ni can be split up into this product, and we know each term in this product is coprime to ni. And if each term is coprime to ni, then it must be the case that the entire product, which is the number n over ni, is coprime to ni. So n over ni and ni are coprime. And if that's the case, we know by the theorem that we just proved, there exists a certain bi such that when multiplying it by n over ni, we get that this is congruent to 1 mod ni. We know that there exists a bi that satisfies this because of what we just proved. And we also know that this obviously is congruent to 0 mod n over ni, because it's just some whole number bi multiplied by n over ni. Meaning that, and this is also ending bi over ni congruent to 0 mod n over ni. And that's it. That's our number. Our number mi is equal to n times bi over ni, when bi is the inverse of n over ni mod ni. So now we prove the existence of mi. So we know for all I between 1 and k, mi exists. Now we will use it to show that x exists, the original x. So again, let's clean the board and do that. And let's clean the board and do that, and then we'll only need to prove singularity for x mod n, and then we'll finish off, and then that will finish off the proof. Okay, so now let's quickly remember what x satisfies. X is congruent to R1 mod N1 is congruent to R2 mod N2, and so on until x being congruent to RK mod NK. And generally we can simply write this: x is congruent to Ri mod Ni. So now we know the existence of mi, which satisfies that R1 and R2 and R3. So basically all of these Ri's. So basically all of these R's are equal to 0, except for Ri, which is equal to 1. Now we will use this to define x. Let x be the sum as I goes from 1 to k of mi, which we know exists, times Ri. let's define x this way. Now, let's see if it satisfies our conditions. We know, let's look at this mod rj, just so we don't get confused with the I being the index with I being the index here, mod ri, where I satisfies some constant. Let's look at x mod rj. So x mod rj. So what we can split this up to is mi is m1 times r1 plus m2 times r2 all the way on until mj minus 1 times rj minus 1 plus mj plus 1 times rj plus 1, and so on until we reach the end of mk rk. We know by how we defined m of something to be, we know all of these, m1, m2, up until mj1, and then mj plus 1, mj plus 2, up until mk. All of them are congruent to 0 mod n j, meaning that, and so this goes to 0, this to 0, this to 0, and all of these go to 0. But we all of these go to 0, and then we have another term, which is the j term. So mj times rj. But we know mj is congruent to 1 mod nj, and then by rules of modular arithmetic, we know nj times rj will be congruent to rj mod nj, meaning that this is equal to rj when we're talking about mod nj. And so x is congruent to rj mod nj, and this holds true for all j between 1 and k, meaning that this we proved that this certain x exists. So now I will quickly prove that x mod n is singular. So what we're going to do is assume there are two numbers, x and y, that satisfy these conditions, and then we're going to show that that must imply that x and y have to be the same number, mod n. So let's begin. So x is congruent to ri mod ni for all I between 1 and k, and same thing for y. It's congruent to ri mod ni. Now what we can do is to look at x minus y. So x minus y, what is it congruent to? Mod ni. Well, if x is congruent to ri and y is also congruent to ri, when we subtract them, we'll get that these are all 0 mod ni. Mod ni for all I between 1 and k. And because all of those numbers are co-prime in couples, n1, n2, and so on until nk, we can multiply them all to get that x minus y is congruent to 0 mod the product of n1 up until nk, which is n. Meaning that x is congruent to y mod n. And that's the proof of the singularity. We choose numbers, two whole numbers, that the only thing we know about them is that they satisfy these conditions for all I between 1 and k. Then we subtract them, and then because all of these are co-prime couples, we can multiply them all, and then we finally get x is congruent to y mod n, meaning that both of them are congruent to the same number mod n. And that finishes off our proof of the Chinese remainder theorem. So that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.